Hi, today we'll be looking at a concept which will help us predict what our circuits will do before even assembling them. That concept is Ohm's law. It shows the relation between voltage, current, and resistance. The base formula for Ohm's law is V equal to I into R, or voltage equal to current into resistance. The variables can then be interchanged to achieve different forms of the base formula. To remember all of these forms, there is a method called the Ohms pyramid. The Ohms pyramid is a triangle divided into three sections with V at the top and IR at the bottom. The line between V and IR represents a division equation, while the line between I and R represents a multiplication equation. To use the Ohms pyramid, you simply cover up the variable you want to calculate, and the equation formed by the other two variables is the formula. This pyramid method is also applicable to any other formula with three variables, like for example, force equal to mass into acceleration. So when we cover V, R and I represent a multiplication equation, so V equal to IR. When we cover R, we can see that V and I represent a division equation, so R equal to V by R. And finally, when we cover I, we can see that the equation becomes I equal to V by R. Now, to understand how to implement Ohm's law, we will now solve a sample circuit. Here we can see that we have a 12-volt power supply, a resistor, and a motor rated for 5 volts at 100 milliamps. We have to calculate the value of the resistor. To calculate the value of the resistor, we will begin by first calculating the voltage the resistor will have to consume. To do that, we will subtract the voltage that the load will consume from the supply voltage, which in this case gives us an answer of 7 volts. Next, we convert milliamperes to amperes. This is because it is compulsory to use SI units when using Ohm's law. So 100 milliamps is equal to zero point 0.1 amps. Now that we have the values for both the voltage and the current, we can find the required resistance with the base formula R equal to V by I, which yields us with the value of 70 ohms. So a resistor with a value of 70 ohms must be used. Now let's do a briefing of our first practical demo. We will be using an LED with a forward voltage of 2 volts. The forward voltage is the voltage that the LED will consume. The LED will also have a rated current of 20 milliamps. This will all be connected to a 5-volt power supply with a resistor. The value of the resistor will be 150 ohms as calculated on the screen. We will measure the voltage consumed by the LED and the current flowing through the circuit with a multimeter. Here we have the circuit assembled on a breadboard. The multimeter is set to measure the voltage consumed by the LED. When we turn the power supply on, we can see that there is a voltage drop of just about 2 volts, which is exactly what we had calculated. And now the multimeter will measure the current flowing through the circuit. As you can see, the current is just around 20 milliamps, which is exactly what we had calculated. Okay, now moving on to our second demo. The second demo is pretty similar to the first one, except this time we are using an LED with a forward voltage of 2.8 volts. This time the result is that we should use a 110 ohms resistor, but since resistors with that exact value are hard to find, we will have to round the value off. One thing to remember when rounding off is that we should always round off to a greater value. That's because it is occasionally okay if your loads gets less current than anticipated. But if it gets more current than anticipated, you could risk damaging it. So, we'll be using a resistor with a value of 120 ohms. We have the circuit assembled on the breadboard here. And when we give it power, we can see a voltage drop of 2.8 volts. And when we switch to current measuring mode, we can see that there is a current of approximately 18 milliamps, which is because we rounded the value of the resistor off. Now we'll see how we can combine the formula for wattage with the Ohm's law formulas. Wattage is the overall electrical power flowing through the circuit. Wattage is represented as a P for power in formulas. The formula for calculating wattage is P equal to V into I. And when we merge this formula with Ohm's law, we get two more formulas, which are power equal to voltage squared divided by R and power equal to current square multiplied by R. A resistor is rated to handle a certain maximum power or wattage. If this value is exceeded, the resistor may get damaged and cause harm to other components. So it's crucial to be within these limits. To better understand how to calculate the consumed wattage of a resistor in a circuit, let's look back at our first example circuit. The wattage comes out to be 0.06 watts according to the calculations on the screen for that circuit. So, we can safely use any resistor with a wattage above 0.06 watts in that circuit. And this is what happens when you or overload a resistor. Now you may have noticed that in some cases the value shown by the multimeter was slightly off than the one we had calculated. This is caused by the passive resistance present in wires. It is practically impossible for any material to have zero resistance. Even if it is not meant to be a resistor, it will have a resistance. This passive resistance in wires gets quite noticeable in large lengths of wires. As shown here by the multimeter, a wire of length 50 cm has a resistance of 3.8 ohms. This is not an accurate representation at all, but it shows that there is a resistance present in wires. The wire gauge is the thickness of a wire. The American wire gauge or AWG is commonly used to denote wire thickness. The higher the AWG, the thicker the conductor is. A higher AWG means a lower resistance. Of course, with larger lengths, the resistance also increases. Thanks for watching this video. Hope you learned something new. And if you enjoyed watching this video, please subscribe to my channel so I can keep on uploading videos like this.